Hello and welcome to part 1 of Dev Maths and Stats Refresher Course Lecture 10. And in this final lecture we put together what we've learned about probability and random variables and distributions and sampling to come up with a number of different tests, and I'll show you some examples of applying those particular tests. But before we do that, we'll look at some ideas to do with samples and probability and how that lets you do inference in general, in a way that applies to any test at all, including tests that we won't do today, that you'll do in future. So here are some general principles. Now in all these examples, the idea is that you should pause the video and think about the question before you carry on. So I've got about 4 or 5 different examples. So let's start then with the first one. So first of all, we're looking at fertilizer vouchers, for example, in the farm input subsidy program in Malawi and other areas now. So we've got 2 rural areas, A and B. And these, imagine that, are quite large rural areas, perhaps in Malawi or elsewhere. And within each area, you have a random sample of children who are going to be weighed and measured. So the children in area A will get, area A, all of area A gets vouchers for fertilizers. All of area B does not. So 2 years later, you select the same children as previously and re-measure them and work out what was the increase in body mass index for each of those children in the sample. So sample from area A and sample from area B measured at the start and 2 years later, and you look at the increase in body mass index. And let's say we find this. So in area A and B, 34 children in each sample. This is the mean increase in body index. The mean increase is 0.76 in area A and 0.38 in area B. And this is the standard deviation of the mean increase. Okay, what can we conclude from these results? Here's your first question. Will we conclude that the children's mean BMI increased more in area A than it did in area B? What do you think? So have a think, pause the video. Okay, so you should write down your answer, whether you think yes, no, maybe to that, because we're going to come back to these later. Okay, the next question is, from the same data, can we conclude that the fertilizer vouchers had a positive effect on child nutrition in area A? Okay, pause the video if you want. Write down what you think the answer would be for that on a piece of paper, and then we'll carry on to the next example. Next example is about the impact of education, or the possible impact of education on entrepreneurs and business. So the study is informal sector traders in a city. Randomly select 486 traders for interview, and you find that 104 of them have completed secondary education. So we said they have secondary education, the other people don't. All of those people, all 486, are asked to record their daily turnover in their business. After 1 month, you collect the data, and this is what we found. So this is in Uyghurs per day, so you might work out what that is. But among those who had not completed secondary education, this was the turnover, 763.23. Among those who had completed, this was the mean turnover, 767.62 for those with secondary education. How should we interpret these findings? So here's the first question. Does this show us that informal traders in the city with secondary education have higher mean turnover than the informal traders in the city without secondary education? So what do you think the answer to that? Write down your answer to that. Pause the video if you need to. Next question is, do these findings show that secondary education tends to raise the turnover of informal traders? What do you think the answer to that one will be? Then we'll carry on. And now the third example, the 1 laptop per child policy that was started off by Nicholas Negroponte, who was one of the early American computer science pioneers, technologist, also founded Wired magazine. And he had the idea in the early 2000s of creating very, very cheap laptops, which could be powered by, I think, winding up instead of electricity supplies for under $100, which was incredibly cheap at the time, and started experimenting with distributing them to developing country children. So some trials have been carried out on the effectiveness of this in different places. One of the early well-known ones was schools in a South American country were selected, and 320 schools in all were chosen, and all the children in all 320 schools are given a set of standard tests in, I think, maths and English, and then about half of those schools are selected completely at random, and those schools were enrolled in the one laptop per child policy. So each child got one of these cheap laptops. And then after 1 year, the tests are repeated in all the schools, with and without the laptops. And the findings were like this. So what do these figures provide evidence of? So here we have two different areas. We've got maths and reading. So this is the mean rise in reading score. Schools without laptops, schools with laptops. Mean rise in maths score, without laptops, with the laptops. So what does this data, or these figures, provide us with evidence of? Again, so here, think about your answers to these questions and jot down your answer. There's more options this time. So do the results suggest that in the schools that received the laptops, English scores rose more than in the schools without the laptops? Maths scores rose more than in the schools without laptops? Both maths and English rose more in schools with laptops compared to schools without, or none of those things. So all these comparisons are comparing schools with laptops to those that did not get laptops. Would you go for A, B, C or D? So just pause if you want and jot down what you think. Go on to the final. Slides are freezing. The final question, do you think the schools suggest that, do the results suggest that the laptops given to selected schools helped the English scores to rise? Or did the laptops help the maths score to rise? Did they help both the scores to rise? Or again, none of the above? So write down what you think you'll put for that. Pause if you like, so A, B, C or D. And then we'll go back and look over some of these again. Okay, so statistical analysis and simple tests can help to answer some of those questions above. And what we do is we calculate some probabilities, and they help us to test different assumptions. And the assumptions we tend to call hypotheses when we do the tests, as we'll see when we do the examples. So calculate probabilities and use those to test different assumptions. For example, fertilizer vouchers. Now, go back to the first one. What can we conclude from these results? Yeah, so we see that in this sample of children, there seems to be a bigger increase in the BMI in the sample from area A compared to the sample from area B. So we need an assumption to test, a hypothesis to test. So what we do here is we start by assuming that the mean BMI increase was actually the same among children in both regions. So this is really the most crucial thing to understand, is how is this possible? Is this just contradicted by these figures? Is it possible for this to be true and for this to be true? So just think about that and pause for a second. Is it possible for this and this to be true? And of course, yes, the answer is, it is possible for this to be true, because this sentence here applies to the children in both regions, all of the children in both regions, which could be hundreds or thousands or tens of thousands of children. These figures here only apply to 68 children, 34 from A and 34 from B. So it's completely possible that the mean BMI increase can be the same among the children in both regions as a whole, and still, when we take our sample, we find the difference. So what we do is then we assume that this is true, that actual fact in the whole region A and B, the BMI increase was actually the same. The mean BMI increase was the same. If we conclude that, then what we can do then is a calculation which gives us this. And I will show you how you calculate this later on, but it gives us what I call a surprisometer, which measures how surprising it is. So it shows us how surprising it is if there is really no difference between the mean in the whole population in region A and B, how surprising it is that in the sample we find a difference as big as this. And it's like, okay, over here it's not surprising, very likely. This is 50-50 chance. This is extremely unlikely down this end. This is, okay, 25%, 30 chance. It's not very unlikely, slightly unlikely. So what would we do here? So again, look back at your answer, and what would you conclude from these results? That do you think that this does show us this data in the sample? If we have this calculation, does that show us that children's mean BMI really increased more in area A than in area B? And my answer, and most statisticians' answer, would be here that no, it doesn't show this, because if we assume that, in fact, in the whole of area A and whole of area B, the mean increase was actually exactly the same, then how surprising is it we can choose a sample of 34 from each area and find this much difference in the mean? It's not very surprising. It could happen. 25% chance that could happen. So this difference here, this is telling us that it could just be a random chance. So it's not so surprising. So I cannot say to myself, I'm sure that there is a difference in area B and area B, area A and area B in the whole of the population of children. So this does not really show me very much about all the children in area A and B. It just applies to the sample. Okay. As for the other question here was, does this show that the fertilizers caused an increase in this increase in BMI of the children, even in the sample? And of course, we can't conclude. I mean, we don't know that there was an increase in the whole area, as we've just shown, and even within this sample, it's just a correlation. It could just be chance that we happen to pick ones that have increased, or there are so many other factors that could have been causing these particular children to increase their nutrition in area A but not in area B. So it's a case of correlation rather than causation. So no, we definitely can't claim that the fertilizers had any effect on the basis of this. Okay, and on to the next example. The educated entrepreneurs. So here you found that this was the turnover without secondary education. This is with secondary education. How can we interpret these findings? Well, again, you make an assumption, which is, okay, these are the 400 and something people that we talked to, but if we look at all the traders in the city, we assume there's no difference in the mean turnover in all the traders between those with secondary education and without secondary education. And if you assume that, you can then calculate this, that if you assume that in the whole city there's no difference between these two groups, then the chance of finding a difference as big as this difference here is very, very unlikely. It's like way less than 5%. It's like down about 1%. So it's around about 1 in 100 or less. So in that case, we can conclude. What do you think? So again, pause for a moment and write down what you think you would conclude in this situation. Okay, I hope you've thought about that. Well, again, most analysts, most statisticians would conclude from this that, yes, here we can be quite confident that the informal traders in the city with secondary education do have higher mean turnover than those without. Because if we assume there's no difference between the groups, then we have to accept that this difference happened, which was so incredibly unlikely. Yeah, it means it was the sample we got was very, very unlikely if we assume that, in fact, that there isn't a difference. So we'd say, yeah, I think this does show us there is a difference in the city between the two groups. Now moving on to the last example, the one laptop per child, and doing a similar calculation. What do these figures provide evidence of? Well, here the assumption is different. The assumption here is that laptops have no effect on scores, because the two questions I initially asked you, in the other cases, it was the one about effect. It was the one about effect. What I did not conclude there in the previous one was that even though we can conclude that people in the whole city have got, with secondary education, have got higher mean turnover than those without, in all the traders, we can't conclude that this has been caused by the secondary education, because there are many other things that could be different about those two groups. It's just simply a correlation. For example, it could be that people that have got good family connections are more likely both to have got better business and to have completed secondary education, and so on. There are many different routes of causality that can explain this correlation. So we can't at all be confident about that. But we can be confident there is just a difference between the two groups. But when it comes to the other situation, this one here, well, here again I'm asking, does this provide evidence that in all the schools, the ones with laptops did better in maths and English? Well, yes, it does in this case, because in this case we have all the schools. It's not a case of working out what's happening to other schools. We're not sampling from other schools. All the schools in the country, 320, have been divided in two randomly, and we can see from the data, unless we have measured it incorrectly, that yes, there was a bigger increase in reading score and a bigger increase in math score. So there's no doubt there. The question in this case is, was it caused by the laptops? And in this case, because it was, although there are many other factors that would possibly influence the reading score change and the math score change among these children, because it's randomly been assigned between the two groups, all those other factors that could possibly have affected it, including ones we can't even imagine, they would also be randomly distributed between the two groups. So they can only have a random effect on the difference in the reading score and the math score. So here, again, the question is, could this difference have occurred randomly or not? And if it doesn't occur randomly, then it must have been the one thing we know was systematically different, which is the laptop effect. And again, you'll study this ad infinitum when you get onto things like randomized controlled trials, because the random allocation means that if there is a difference, it must be caused by the laptops. So the two possible explanations here are, either this has just occurred by chance, because of those unknown factors that were randomly distributed between the two groups, or if it's too big a difference to be explained by chance, then there must actually be an effect from laptops. So here the assumption is subtly different, but the method is exactly the same. So here the assumption is that the laptops had no effect on scores. So the difference we're seeing is just random. If you make that assumption, then these are the two things we get. Taking reading, if laptops had no effect, then the chance of getting this big a difference randomly was very, very unlikely. It's well below 5%. Whereas on the maths side, if the laptops had no effect, the chance of getting a difference as big as this just through random variation is, yeah, about 30-odd%, so 1 in 3 or so. So that's quite believable. So here we have kind of different conclusions. So what would you think about what you'd go for here again? Pause if you like. And okay, I hope you pause that. But here, the conclusion would be that we can be confident that there was a causality causing the English scores to rise, because it's very surprising for that to happen if we assume that laptops had no effect. It's incredibly unlikely to see as big a rise as we saw there. But with the maths, yeah, that could just be random. So you can't be sure about this one, so it's A. You've got evidence of causality causing the English scores to rise. So the interpretation of the test is different. Sometimes you're trying to show, is there a causal effect? Other times you're trying to show, is the effect you're seeing in the sample applying outside the sample? But the way you interpret the results is the same. So let's get on to the final conclusions of this. This, I claim, this pattern is the basis of all statistics tests that you're going to do. So the three things you have are a theory about the world. So some assumption you make, and when you get onto the technical examples of this, we'll call this a hypothesis. So you've got a theory or hypothesis about the world, and then you get some data, you see something happening. And the key thing is, mathematically, you need to work out if your theory is correct, what's the probability that you're going to see this observation? And if the probability is quite high, then you say, oh, okay, I'm happy with this theory because the observation I'm seeing is quite likely if I have this theory. But when this surprisometer gets down into this red area here, you think to yourself, I'm not happy with my theory, because if my theory is true, then I have to accept that some very, very surprising and unlikely observation is happening. And if it's too surprising, then I have to think to myself, hey, this theory must be rejected, it can't be correct. Of course, there are other possibilities. It could be observation is incorrect, so you have to check the observation carefully. But if you're confident about the observation, and it's very, very surprising, then you have to think about rejecting the theory. And that's the basis of all these tests that we'll do. So let's just show you two of those examples back in this. Some words to say. Two of these examples back in here. So in the first one we had the theory about the world we'd assume is, okay, we'd assume as our hypothesis that the children's mean BMI increase in areas A and B was the same. That's all the thousands of children. We assume it's the same. Then what we observed was these 34 children in the sample with an increase in area A of those 34 children of this, and area B of this. We say, okay, how surprising is it if I make this assumption that I'm going to get 34 children from A and 34 children from B with this much difference? And it turned out that yeah, that could happen. It's not too surprising. So because the theory doesn't make that observation too unlikely, we can't reject it. So it could well be that this is true. So we can't draw any conclusions about differences in A and B and from that one then, that example. But then the other one, the second example, the theory about the world is that in this whole city, all the informal traders without and with secondary education have the same mean turnover. So the means of those two groups are the same if I take all those thousands of traders. If that is true, how likely is this observation which we had, which was we sampled about 300 in one group and 100 in another group. Those with secondary education had this turnover in the sample, those without secondary education had this turnover in the sample, and you can calculate that if this assumption is correct, the observation has very, very low probabilities, very, very surprising. So because I just can't believe that something so very surprising has happened, I prefer to say, no, I think this theory must be wrong. So I reject that theory, and that's what we do. So the assumed theory does make the observation very, very unlikely, so we reject that theory. Okay, so that then is the basis of all statistical tests that you're likely to meet. How likely? Great, fantastic, very, very useful. So the question remains is how do you calculate this probability? How do you make a surprisometer or a test of various sorts? And that is where we just, in the subsequent part of the lecture, just put together the theory of random values, random variables, distributions and probability and sampling. And that lets you work out what these probabilities are in any particular scenario. And that varies from different case to different case. But the general principle is the same. It's really, this applies for all cases. But the question is, how do you work out the probabilities, which we'll see in the next part of the lecture. And then we'll do some examples. But for now, thanks for watching.